Here's your flipped lesson on double displacement reactions. So the definition right from your notes on your blue sheet. In general, all double displacement reactions take place to some extent. They will go to completion if a gas is given off, and we would represent that with an up arrow, or if a precipitate is formed, and we would represent that with a down arrow. We're going to check our solubility rules, which I will teach you how to use in this video, to see if a precipitate will be formed. If there's no precipitate, we would say there's a no reaction, or NR. In a double displacement reaction, two compounds exchange partners. One of these things can be polyatomic with each other to produce two different compounds. So we would say AB, compound AB plus CD, would yield AD plus CB. Don't get too hung up on the variables if that's confusing right now, but just think about it like this. A and B are compounds, so A would be positive and B would be negative, because we know that all of our ionic compounds are always going to have the cation be first in the naming. So A would just switch with the opposite negative anion, so that's why A and D would go together. Please note, it's never going to look like this, where our two pluses and our two minuses go together in a double displacement reaction. So you're basically swapping dance partners in a double displacement reaction, but A is never going to go with C. So A and C are never going to go dancing together. Alright, here's our solubility rules. What I would do is pause the video and write in all of those ions so it helps you recognize them a little bit better. Alright, hopefully you've written in all of your ions here, and the solubility rules are on the bright yellow sheet of paper, and it'll help us figure out if a double displacement reaction has produced a precipitate. And so take a second and read through this, but I have some examples as well. Please note that these are neither all-inclusive or infallible. There are always exceptions to the rule, but for the most part, these will work for what we have to do. So a little bit of vocabulary terms to help us. Soluble means it will dissolve. Insoluble means it will not dissolve. So when I have something that's soluble, I would denote it with an AQ, which means aqueous. So aqueous is a compound that's soluble in water. It's split up into ions. If it's insoluble, it means it will not dissolve. We would represent that with an arrow down. Insoluble and precipitate go together because that means that it's something that has formed a solid. And then no reaction, NR, just simply means that no reaction has happened. So in this case, with a double displacement reaction, it means that both products are soluble. So if we're looking at our solubility rule application, so I just kind of took a screenshot of the solubility rules so we have them to reference here. So if I'm looking at silver nitrate and trying to figure out if it's soluble, what we look at is silver is solubility rule 3, so there's silver right there. And then nitrate is solubility rule 2, and there's nitrate. So silver tells us it is insoluble, but the nitrates tell us it's soluble. So from our knowledge of the solubility rules, we know that it would be soluble because rule 2 comes before rule 3, and so silver nitrate would be soluble. And we would write it like this, AgNO3, and then we could denote it as soluble by putting that state of matter, aqueous, next to it. So another solubility rule example here, lead chloride, lead 2 chloride to be specific. So lead is solubility rule 3, and it's insoluble, and chloride is solubility rule 4. So because rule 3 is above rule 4, this would be insoluble, and so we would write it with an arrow down on the right side of the equation. So PbCl2 would have an arrow down. You might also see a solid state of matter represented there, but most of the time what we're going to do is just look at that arrow down representing that we have formed a solid. So think about it like this. If you see an arrow down, think I've got a solid substance, a chunky monkey, if you will, formed at the bottom of the container that I'm dealing with. So from your types of reactions packet, number 33 is our double displacement start. So here's how I would like for you to do your double displacement reactions. So you're going to get this example down, and then we're going to practice the rest in class together. So first you want to write the charges above the words for the reactants, and that should be old news. You should know that that's exactly what you're doing for all of these all the time. So we're going to write our charges above the words here, so we know barium's a +2 and chlorine's a -1, sodium's a +1 and sulfate's a -2. Then it's easiest to write your reactant formulas. So I'm going to go ahead and do my crossovers and write my formulas here. This way I like writing the reactant chemical formulas here because then that helps me figure out my variables so that I can switch them. So in this case, barium would never combine with sodium because those are both positively charged. ions, and so barium has to recombine with sulfate. So then once you figure out what your recombination is, you can create your product formula in words and then put your charges above those words, just like we always do. So if I have barium sulfate and sodium chloride, I would put the charges above the words, cross over, and make my formula. So hopefully you're familiar now. Anytime you do this, you've always got to check to make sure you're balanced. So I would balance the equation with a 2 in front of the NaCl. And then lastly, what we're going to do is look at our solubility rules and figure out what makes our precipitate, if either do. And so barium we know is rule 6. It's insoluble. It's actually one of the exceptions. Barium sulfate is insoluble. And so I would put an arrow down next to the barium sulfate. And I know that sodium is always rule 1. So anything that's combined with sodium will always be aqueous. So we can put aqueous state of matter to the right side of the equation there. And then last but not least, it's worth getting down these couple of examples on your blue sheet for what happens when we switch and get the same compound. So for metal oxides and water, so for sodium oxide and water, for example, if we were to switch these, we would end up getting the same thing. We would get sodium oxide and water. So when that happens, we actually combine it, and it combines to then form a synthesis reaction. So it would be a metal hydroxide. So it would look like this. It would be sodium oxide and water, and it would combine to form sodium hydroxide. And then we would balance it to get our final reaction. The other example is if we have a non-metal oxide and water, and it will form an acid. And so here, if I switch it, it becomes the same thing. And so I just simply do a synthesis reaction now, and I combine the H2O and CO2 to become what I call carbonic acid. So notice all I did was take the C, there's my C, there's my two H's, 1, 2, 3 oxygens, and there you go. So thank you for coming with these notes ready and written down on your blue sheet, as well as the example on your types of reactions packet.